Welcome. I'm going to talk about auditory masking today. And before I do that, I will start with a short presentation of myself. My name is Torben Poulsen, and I have been working at the Technical University of Denmark for many years. I have been working with teaching and research within these areas here: psychoacoustics, audiology, audiometry, acoustic communication, speech intelligibility, hearing protectors, noise and hearing loss, and also something about noise annoyance. So that's the area that I have been involved in for many, many years. I'm a member of a working group in the International Standardization Organization, working group number 1, which is threshold of hearing. That's the name of the working group, and it's a working group under Technical Committee 43, which is acoustics. Threshold of hearing, that's actually the background for everything that you're doing here in acoustics. All audiometers and so on are based on the data, or the calibration of those instruments at least, are based on what we are doing in that working group. I'm also a member of another working group, number 17, not under 43, but under a subcommittee under 43, a noise subcommittee, and this is concerned with measuring method for hearing protector attenuation. I'm not going to talk about hearing protectors today. So now it was auditory masking. And I'm going to talk about what masking is, the concept of upward spread of masking, the motion of basilar membrane in the inner ear, which is very closely related to masking, something called complete masking, and something called partial masking, and some temporal aspects also on this. Finally, something about hearing impairment and masking. So, what is masking? Masking is complete masking. For example, that means a sound, that's the masker, can mask another sound. That means make it, the other sound, inaudible. So you have a sound, bzzz, and that sound can mask another sound, a faint sound, so that you cannot hear that faint sound. That's the complete masking. Partial masking, a sound can influence the loudness of another sound, and that will typically reduce the loudness of another sound. Central masking, a sound in one ear can influence the perception of sound in the opposite ear. This has something to do with audiometry. If you're putting sound in one ear, measuring the hearing threshold in one ear, and you will typically put in some masking signal in the other ear, and that masking signal can, through the nervous system, the central nervous system, can have an influence on what's going on in the test ear. I'm not going to talk about masking in a clinical sense. I'm not going to talk about how to adjust the masking level for contralateral masking, but I will just mention this central masking phenomenon. And what's more, simultaneous masking. The masker and the mask sound are present at the same time. Those two are there at the same time. Forward masking, that's masking that takes place after the masker has stopped. That means forward in time. So we have a signal that is a masker, and then the signal stops, but there will still be some masking after that signal. That's the forward masking. The backward masking, that takes place the other way around. Before the masker begins, that sounds curious, but you can actually have backward in time, some masking. You can think about listening to a very faint sound and then a big sound starts. But actually that big sound will give you a masking back in time so that it is difficult to hear what's going on just before the big sound starts. And that has something to do with the way our nervous system works. Upward spread of masking. We have a figure here with a frequency axis there, sound pressure level scale over here, axis here for that, and the green curve here is the hearing threshold. In conditions where you are sitting in a typically anechoic room, having the signal coming in frontally into you from a loudspeaker at some distance, 2, 3, 4 meters, you're listening with both ears. There's no background noise, there's no ambient noise, no reflections, nothing, only that signal coming into you. Then you will see such a hearing threshold like this. And one thing that you could see is that for low frequencies down here, the hearing threshold increase, so you need much more signal in order to be able to come up to that hearing threshold. In order to be able to hear it, you need some sound pressure level. Very little over here. Here, this little dip over here, around 3-4 kilohertz. That's the resonance of the ear canal. And you can see you can get sound pressure levels, decibel values that are actually negative. There's a 0 there. So here, where we are most sensitive, the hearing threshold is at negative decibel values. Don't be confused. You can easily have negative decibel values, and it's still a sound. It's a faint sound, but it's still a sound. Up here in the other end, we have the pain threshold, or whatever it may be called. But up here, you will actually feel some pain in your ears when the signal is that loud. And the little one there is what we will call an uncomfortable level. That's the dynamic range of our hearing, so to speak. But now let's try to go into masking in more detail. This blue curve is the same as the green one that you just saw before. And how do we measure such a curve like this? We will take a tone. No, I think I will use this one just for a while. Take this one. I will take a signal, let's say 100 hertz, and then I will turn up my signal. Up, now I can hear it. Then I will make a cross there and say, okay, now I heard that frequency. Then I will go to another frequency and I will turn it up until I can just hear it. That was there. I'll make a cross there. And I'll do so for all the different frequencies. Find out how much level do I need in order for that signal to be heard up here. And then I will get such a curve like this. And as I said before, here at low levels, low frequencies, not low levels, low frequencies, you need, for example, here at very low, about 60 decibel sound pressure level, just to be able to hear it. Not to hear it clearly, but just to detect that here is a signal. Now I will come with another signal. I think it's green. It's a little bit different than the other one, but here we have some green signal. And I have that signal all the time. It's on all the time. Then I will try to measure my hearing threshold once more. And I will do like this, as I did before. Oh, there, and oh, this is not right. The result will be like this. So I will give it there, not there. I will come up to this place, and up to this place, and up to this place, and there, and there, and there, and there. So my hearing threshold, when this signal is present, is changed and will go like that. Now I can increase my signal here a little bit, then my hearing threshold will go like that. It's called the masked hearing threshold. And the funny thing here is that such a sound, this sound here, can mask another sound, make it inaudible. For example, this sound that is over here. That sound would be clearly audible if I removed the green one. If I took that away, then I will be very clearly above the threshold. But I'm not above the threshold. Now when I have this green signal, my hearing threshold will go up like that. So this signal is inaudible even in a situation where this is at another frequency than this one. It's not, has nothing to do with the width of this signal here. It's inaudible also at places where this green signal is not present. I can increase it even more, and then I'll get something like this, still a masked threshold, and I can increase it even more. Now it's really almost 120, so it's very, very loud sound. But the masking will go up like that. And one of the things that you shall see here is the upward spread of masking. This green signal will mask upwards in frequency. Not very much downwards in frequency. It's almost only upwards in frequency. It's not the other way around. So that's the background for the upward spread of masking. Masking is spreading upwards. Yeah. How does this come? Let's just go back for a while to what you have learned in school, I guess. Here, the outer ear, the ear canal, the tympanic membrane, the middle ear with the 3 bones in there, and the inner ear, the cochlea here. Nerve connections up to the brain and from the brain, and the vestibular system, the balance organ, sitting there. Now I will try to go into the cochlea and look at the basilar membrane movement in the cochlea. And in order to make it easy to see what's going on, it's an uncoiled drawing. Take the cochlea, which is such a snail house shaped thing, and you can stretch it out, and that's what we see here. Here we have down at the base, the bottom of the cochlea, and this is the top of the cochlea. Don't be confused of the width of all these things. Up in the top, the snail house is narrow, but at the base, the house is such snail house is wide, but the basilar membrane is not that wide down there. It's the same we have over here, and this is a 6 kilohertz tone, and what is illustrated is the movement of the basilar membrane for a 6 kilohertz tone. There will be movements in the middle of the basilar membrane, not at this place, not up there, but in the middle. If we look at this one, which is similar drawing as the other one, then we can see that the low frequencies will give movements up at the top of the cochlea. The high frequencies will give movements at the bottom of the cochlea. So there's a frequency analyzer in our cochlea, in our inner ear. And this can be illustrated here. And one thing I could say already, there are hair cells along the basilar membrane. They are sitting along on top of the basilar membrane, so to speak. And when the basilar membrane moves, then the hair cells will be moved too, and there will be nerve impulses that are sent to the brain. Now I shall try to start those two things over there. Let's see. This is a model calculation for a 250 Hertz tone. You heard the tone a little. And you can see how the movements takes place at one end of the basilar membrane. Not down here, but all up there. Then let's take the other one. Again, see how all the movements are here and nothing up there. So in a very narrow area, you will have movements for such a certain frequency. Now they became black, unfortunately. But let's go on to the next one where we have a similar thing. Now we have a signal of 400 Hertz and 1600 and 6400 Hertz at the same time. All these three frequencies at the same time. It may look like that if you look at a scope or on a computer, but on the basilar membrane, it will give movements of the basilar membrane like this. Now it's turned the other way around and compared to the slide that you just saw. We have the low frequencies here, which is up at the top of the cochlea, but in order to make it look like a usual frequency axis, we have the 400 Hertz there, the 1600 Hertz there, and the 6400 Hertz there, and you will have movements like it's shown over there. If you look at the envelope of those movements, that one, you have similar envelopes here and also over here. Look at that envelope, and then I'll show you the one that you just saw. Then you can see again something that are very steep towards the low frequencies and less steep towards the higher frequencies. So what we see here from a psychoacoustic experiment is a picture of the basilar membrane movement. It's fantastic. I think it's fantastic that you can go in and do some measurements like this and then say, that's my basilar membrane that goes like that. It's actually a nice picture of that. Complete masking. Here we have again this threshold, the absolute threshold as it is called, and if I put in some narrow bands of noise, then it will look like this. Something like there, something there, something there, and you can see a fairly steep slope here and a less steep slope towards the higher frequencies. Also, it's not that clear on that one, but you may say that the curves have almost the same shape, this asymmetrical shape. If I do the same thing, do such a mass threshold determination with a pure tone, having one pure tone, 1 kilohertz in this case, at different levels, then you will see the picture that you almost saw when I tried to explain this masking things with these levels. And the reason why there are some problems up here, that's just some interference between the constant tone, which is 1 kilohertz in this case, and the test tone that you are using in order to find out where is the threshold. You'll have some beating between those two tones. But the principle is the same. The picture is the same. If you go to a broadband noise, white noise at different levels, then you will see such masking thresholds like this. Some that are almost frequency independent up to about 500 hertz or 1 kilohertz, and then they change a little, 10 dB per decade, as it's indicated there. And the reason why they are not just straight or horizontal, if I may use that word, has something to do with the width of the auditory filters. I'm not going to talk about auditory filters right now, but this is actually a picture of how the width of the auditory filters become wider and wider when you come up in frequency. Partial masking. If a sound does not mask another sound completely, then we talk about partial masking. Here you have a sound, and you can think about having another sound, a masker, that does not mask that green one totally, but only partial. And that will have an influence of the loudness of the green one here. I have used an example about a car radio, and that example was very good back in time when you have very simple radios in cars, where you could turn on the radio and then you drive around in your car, and there will be some noise in the car too, and then you will turn up the radio until you think that the music or speech or whatever you're listening to is comfortable. But then when you stop your car and all that noise around you, the wind noise and tire noise and whatever, engine noise perhaps, then when that disappears, you will think, now the radio is much too loud, and you will have to turn it down. And that's because all this background noise make a partial masking of the sound of the music or the speech from the radio. Today that example may not be that good because modern car radios, they adjust their level according to the speed of the sound. You can simply say, okay, 2-3 dB more per 10 kilometers per hour or something like that. So for modern cars, this example is not that good. But you can, I guess, find other examples in your daily life where someone has some sound that is influenced by another sound. Think about the fan in the kitchen. You have a fan that's exhausting fan, and that's okay. And you're sitting there talking with your wife or who else you're talking with, and sometimes this fan is so loud that you need to raise your voice. But if you turn down or stop the fan, then you can lower your voice and make it more comfortable again. So there's a lot of practical examples where you will see such partial masking. Not complete masking, but just partial masking. Temporal aspects. The temporal aspects is backward and forward masking. Here we have the stimulus, it starts there and it goes on like that, and then the stimulus stops, and we will have some masking. We will have some backward masking that I talked about, but let me start with the other one, which is more understandable. You have some signal here that stops, and the forward masking will go on for a duration of about 200 milliseconds or so. It's just a round number. I wouldn't say that it's precisely 200 milliseconds. It could be 210, or it could be 190 or something like that, but let's not go into details of that at this moment. That's the forward masking. Sometimes it's called post masking because it's after the signal. But there is this backward masking that you can measure too. It's only 20 milliseconds. It's a very short duration phenomena. Backward masking or pre-masking, but backward masking in opposition to forward masking. I'm not going to saying more about this, but you can have the stimulus there, and then you could try to measure the forward masking situation. And what you will do is that you will put up such a little pulse like this, a Gaussian pulse, as a function of duration. So duration, you start there, and then you move this pulse along the time axis here, the delta t, and you measure the threshold of this pulse. And here are some results, actual measured results. It goes like that, and after some time it will come down to the absolute threshold for that pulse. So this is the forward masking situation. And as you can see, 10, 100, it's about 200 there. So the 200 milliseconds is reasonably okay. That's the way it's measured. And you could measure the backward masking in the same way, doing it over here. And then you will get that the curve covers about 20 milliseconds. Masking and hearing impairment. Here we have some measurements, actual measurements on real people. Normal hearing persons, someone has measured absolute threshold for different frequencies from 200 Hertz up to 1 kilohertz. And that's the absolute threshold, no signals apart from this pure tone that you use for that. But then you come up with a narrow band noise here, 500 Hertz center frequency, and an 85 Hertz bandwidth. So it's a narrow band noise that is constantly there, and then you measure the masked threshold, and the signal will go or the result will be like this. You can do the same thing at 4 kilohertz. It's over here, the absolute threshold, and then you put on this narrow band noise at 4 kilohertz. Again, 18% bandwidth. That's about 700 Hertz in bandwidth, and you'll see these curves that looks similar to what I showed just before, with different slopes. It's maybe not that clear in that drawing. That's for normal hearing persons. But now we do the same thing for hearing impaired person. A person or persons with hearing impairment at 4 kilohertz. It could be a noise dip in the audiogram, a noise, hearing impairment at 4 kilohertz. Again, for 500 Hertz, where there's no hearing loss, you will get this one, absolute threshold, and this one. And if you compare the shape of those two masked threshold, you will say, okay, that's the same situation. But over here, where we have the hearing loss for the 4 kilohertz, the absolute threshold is like that. And this one, this figure, this curve goes like this. So there's much more masking for these 4 kilohertz persons than there is for the normal hearing person. So we have a clear difference in the slope of the upward spread of masking for the hearing impaired. This can be boiled down to this situation very schematically: a low pass noise, and for normal hearing you will have a slope of the upper slope of the mask threshold, which is minus 50 dB per octave, about that. But for the hearing impaired, same situation. The upward spread of masking will not go down by 50 dB per octave, but maybe only 12 dB per octave. So that means that a hearing impaired person with a hearing impairment, in this case, example before at 4 kilohertz, a hearing impaired person will have much more upward spread of masking. So to have a hearing impairment is not just a matter of raising the level so that you can hear things. It's much more complicated than that. And one of the complications is this upward spread of masking that is more pronounced for the hearing impaired than it is for the normal hearing persons. This is for frequency. And I think you can imagine also for speech that such upward spread of masking, the vowels, for example, in the speech signals, they are typically rather loud and perhaps also low frequency, and they will give a lot of masking upward in frequency, and that can give even more problems for hearing impaired. Not only their threshold is elevated, but their upward spread of masking is more pronounced. Now we go to another situation. Now it's timing, the forward masking situation. Here, these are also measurements made on real people, some hearing impaired persons and some normal hearing persons, and we are measuring, or those people measured forward masking, the timing. And for normal hearing it would go like that. Normal hearing, 2 kilohertz, 1 kilohertz, but for the hearing impaired it will be less steep for the hearing impaired compared to the normal hearing persons. So not only the upward spread of masking is more pronounced, but also the timing, these forward masking things, that after a signal has stopped, it will last longer for the hearing impaired than for the normal hearing. The threshold for normal hearing listeners decrease faster than for hearing impaired listeners. And that means that the temporal resolution for hearing impaired is reduced. The ability to hear small time-wise details in a signal, a speech signal, for example, is reduced for the hearing impaired. So again, it's not just a matter of a higher level that is needed through a hearing aid, for example, but also this effect is there. Okay, you heard something about masking, the upward spread of masking, motion of the basilar membrane, complete masking, partial masking, temporal aspects, masking and hearing impairment. Thank you for listening.